Let's have a look at practice question set number 17 up on the board here now. The question says, question number 1 says, which of the following unit combinations is appropriate for magnetic field strength? Listen, we know a magnetic field strength is measured in Tesla. Well, none of these are Tesla. It'd be nice if one of them said Tesla because that would be the answer. But what's equivalent to a Tesla? That's what we're looking for really here, is what's equivalent to a Tesla. In order to find what's equivalent to a Tesla, we need an equation that has magnetic field in it, that has Teslas in it. I can think of two. I can think of this one, F is equal to QVB, and I can think of this one, F is equal to ILB. In both cases, what I want to do, no matter which one I use to determine what is equivalent to a Tesla here, I want to rearrange it to solve for magnetic field strength. So the green one here, we're going to say B is equal to F over IL. And we're going to say, for the blue one here, we're going to say B is equal to F over QV. Now, either one of these should get me the correct answer. What I want to do at this point with either of these equations is sub in units for the variables. So if I go with, let's go with the blue one here. Magnetic field is a Tesla. All right. I want to find out if one of these sets of units is equivalent to a Tesla. So let's sub in the units for force and charge and speed. Force is a Newton. Charge is a Coulomb. Speed is a meter per second. Do I see newtons over coulombs times meters per second? No, I don't. But I can simplify this. Let's see what happens when I simplify it. Newtons over coulombs. How do you divide by a fraction? Flip it over. Multiply by the reciprocal. It becomes newtons over coulombs times seconds over meters. Do I see that one there? I do. Look at that. A Tesla is equal to a Newton times second over a Coulomb times meter. The answer is D. Now, let's take a look at the other equation, just in case you chose the other equation to use here. I'm going to say here a Tesla is equal to F is newtons, I is amps, L is meters. Do I see newtons over amps times meters? I don't. In fact, I see two that are remarkably close but can't be correct because they're not exactly the same. If I have the same three variables, it has to look the same. So those two wouldn't work for sure. Even if we didn't know the answer was D yet, we know that the answer is an A or B. Now, C and D both have amps removed and coulombs and seconds tied into it. So let's replace an amp here with a coulomb per second and see what happens. Well, that's newtons divided by coulombs per second times meters. Let's simplify that by multiplying by the reciprocal. I get newtons over meters times seconds over coulombs. Again, multiply by the reciprocal. Sure enough, a Tesla is equal to a Newton times seconds over a meter times coulomb. The answer is D again. How many people did it more or less the blue way? How many people did it more or less the green one? Anybody do it differently? And get the right answer, that is? No? All right. So D is our answer there. Number 1, a current carrying conductor that's this long is placed perpendicular to a magnetic field. Perpendicular is good. Okay, the only thing better would be parallel, because if it's parallel, there is no force, and we're pretty much done, right? If it's perpendicular, there is a force, and we know how to find the force. We know how to find the direction of the force with the hand rule and so on. Has a strength of magnetic field strength of this 20-second time interval, this many electrons pass by. What's the magnitude of the average magnetic force on the conductor? All right. Let's say the force on a conductor is ILB, but I don't know what I is. So I got to find I using Q over T. But I don't know what Q is. So I'm going to find Q by saying I get this many electrons, 7 times 10 to the 19 electrons, times the charge of 1 electron. So whatever that works out to be, for our charge here, we sub into here. We divide it by 20 seconds. We sub that into here. And then we multiply it by the length and by the magnetic field strength, both of which were given. And when we do, we get an answer of, what is it? Yes. Yeah, you're right. 1.34 times 10 to the negative 3. We express that as 1343. Is your hand up? No. And finally, the last question before our break. When an electric current of 10 amp travels through a wire, there's sufficient magnetic force to keep the wire suspended against gravity. Our key word is what here? Suspended. The word suspended means that it must be in a state of equilibrium, and when it's in a state of equilibrium, the forces must balance. Well, we're given a break here because they pretty much tell us what force is balanced, right? We don't have to read between the lines really at all for this. If there's a magnetic field, there's a gravitational field, there must be a magnetic force and a gravitational force. And the magnitudes of those forces are equal to one another. So we'll say I times L times B is equal to M times G. Now we're going to solve for B here. I get mg over I times L. I got the mass here. Do I have the mass? Yep. We're going to convert that to kilograms. So 0.850 times 10 to the minus 3 kilograms. And we're going to convert the length here to meters. We'll say 0.0130 meters. Sub those in, we get a magnetic field strength of 6.41 times 10 to the minus 2, or 641.2.